You're a master. Okay, so I'd like to begin. So for our next speaker, I would like to introduce Enrique Fernandez, except for Enrique Fernandez is not able to be with us here. So Marlise and I have kind of been putting together the presentation to kind of represent him. I'm sure Enrique could do a much better job of doing this, but we'll do the best job we can cover this. So if you look at the kind of the context of the last tutorials, right, then Scott gave you a tutorial at the end of yesterday, right, where he was giving you a more of an optimization controls view, right, a more of a model predictive control approach, right? And he talked about kind of the recent advances there. So that's a powerful set of techniques that we want to be able to leverage in terms of leveraging optimization and online for doing trajectory optimization. And then in your labs, you've had some experience with that, and you worked with one such trajectory optimization routine that we had developed, or a qualitative state planner called Sulu, right? Okay, and then Jorg has told you the amazing progress that's been made in activity planning, right? I'm kind of emerging from the classic problem, which is that you have a set of actions with preconditions and effects on a discrete state space, right? And generating very long sequences, and the power of one heuristic forward search, right? Or a greedy heuristic forward search together with an effective set of heuristics. And Jorg covered the relaxed plan heuristic as one that was early on, but has proven to be quite effective, right? What I'm going to talk about today is how do we bring those two things together, right? In particular, most robotic problems that I've seen, and most real-world problems, you end up having to either plan a motion or you need to plan the trajectory, right? If you're controlling the power grid, it's a trajectory even though it may not be a motion. If it's air vehicles, underwater vehicles, the likes, then it's going to be a motion, right? So for most of these real-world problems, we do need to be able to plan motions, right? But if we want them to be more autonomous, then we don't want to just teleoperate these systems, then we want them to be able to plan the tasks. And so the ability to be able to fold task and motion has been very challenging because each is challenging enough separately, and then you talk about its combination. Okay, so what I'm going to do is to focus on how to pull those together. I'm going to assume that based on what Jorg talked to you about is you are experts at heuristics and heuristic forward search. So I'm not going to talk that much about extending the relaxed plan heuristic into a continuous state world. You can take a look at the tutorial that was given last year by Andrew Coles, which is a very nice job on that, and that's available online. What I'm going to do is to talk about more of thinking about the continuous dynamics, right? How can I think about the continuous dynamics, but over very long time horizons, not short time horizons, and then how does that couple into activities? So I'm actually going to root myself back in Scott's talk, right, rather than Jorg's, and I'll move from Scott's, which is in trajectory optimization, motion planning, and then I'll meet Jorg's at the end if I haven't run out of time, as opposed to starting with the activity planning and moving down, okay? So that's the game plan. So I'm going to give you a fair amount of context at the beginning and kind of give you the big ideas and the motivations, right, during the first, maybe third or so along the way, and then I'll talk to you about kind of the technical details, right, for those who are interested in it. And then I'll also talk about some of the related work, but what I would do is I will actually emphasize more of the related work in trying to bring goals and actions into trajectory optimization, as opposed to the large body of work which has been folding in time and numerical values into activity planning, okay, which is another story. And as I said before, Andrew does that quite well. Okay, so the problem that we're going to look at is mission planning for multiple vehicles. I gave you some motivations at the beginning of the summer school in terms of underwater vehicles, and we're just getting lots of opportunities to do that. We have a mission that we're going to be doing next spring or next summer, right? And it's funded in the context of the NASA's Ocean Worlds program, where what we're doing is we're exploring oceans on other planets, right? Europa is one that for a long time people have talked about, is as an icy surface. Could you get, if the mechanical engineers figure out how to get the submarine there, right, then the computer scientists need to figure out how to make the submarine navigate the oceans of Europa, okay? So this is an example, right, where you have orbiters, surface vehicles, and the underwater vehicles, which will be working in coordination, right? So you can think of it as a multi-vehicle planning. You want to plan over long horizons, and you need to deal with the coupling constraints between the vehicles. You need to both plan your activities, such as a vehicle picking up a sample, right, as well as planning the motions of the manipulator in the vehicle itself. That when you usually think about activities in these kinds of robotic applications, they're not kind of these discrete actions which have just some preconditions effects that influence continuous variables. You have that, right? But usually within a robotic system, you think that you have a set of behaviors, and what you're doing is you're engaging and disengaging those behaviors. And then when you fold in the kinds of optimization that Scott talked about, then not only do you engage a behavior, right? But then what you end up doing is you design a control trajectory for that behavior, right? So usually what you do is, the planning problem is to plan a sequence of behaviors, right? You still have a set of control variables which influence those behaviors continuously, and then what you do is you do the trajectory optimization problem of designing that control sequence, okay? And so that's what you need to do here. And so when we're talking about task and motion planning combined, then we're talking about planning behaviors and then planning the control trajectories for them, okay? So that's our problem. What I'm going to do is I'm going to talk about a particular planner called Scotty, right? And you'll be using Scotty in labs on Wednesday, but it aggregates a lot of different ideas that the communities have been evolving for several decades. Okay, so here's the example mission that we'll be doing next spring. We can't go to Europa, but what we will do is we're going to go to a deep sea volcano called the Columbo volcano, which is right near Santorini in the Grecian islands. And our problem is to explore this caldera. It turns out that in this region, my collaborator has discovered these liquid CO2 pools in a previous visit to an exploration to near Santorini, which is a very strange thing, right? And there's kind of life that feeds on the edge of these liquid CO2 pools. So the purpose of this mission is to do an autonomous mission, right? But the science that we'll be doing is to try to characterize these liquid CO2 pools, vent holes near them, and then try to pick up samples of the lives, right? And then that's the science goal, and then the technology goal is to show that you can do this mission autonomously. Okay, so that's what we're going to be doing. In order to do this, what we'll have is we have a ship, right? Okay, and that ship has a multi-beam, and it'll be mapping the region, and it'll do that for about a month before our actual mission, and then our mission is 2 weeks, right? The first week we had this vehicle, which we've been working with a lot, called a slocum glider. So it looks like a torpedo, but it has no propeller, but it does have wings. And it has a chemical sensor in it, a mass spectrometer. So what it will be doing is to sniff, right, the water, and it will be trying to follow down vent plumes, right? And the glider is a bit funky, right? It can go for very long durations. It can go for a month or longer at a time. And the way that it works is it has called a buoyancy engine, so it can decrease its buoyancy, which causes it to go down. It can tip its nose down because there's a battery that it can move back and forth. So when it wants to move forward, it tips its nose down, right? It reduces its buoyancy, and then the wings push it forward, right? When it gets to the bottom and wants to go up, then it increases its buoyancy, tips its nose up, and goes up. So the nice thing is it only uses energy at the inflection points. So if it can glide for a long period of time, then it's not using any energy during that time. Okay, so that's the concept. It's very uncontrolled, right? So it's very underactuated compared to the currents. So there's a lot of uncertainty and risk. And Ashkan will be talking about risk-bounded kind of motion planning, to deal with those kinds of problems. Okay, so that's the problem, right? But what I want to talk about today is how do we coordinate these vehicles, right, and the activities that they perform each day. So here's an example that I'll use, right? And it's one that we've been developing and demonstrating Scotty for. So we have the caldera, right? We have a region that we need to stay in. We have I guess what I didn't say is the last vehicle is a remotely operated vehicle, which will control autonomously, but it's very controllable, right? It's like a helicopter, right, in terms of maneuverability, and then it has a manipulator to do samples, right? So it's the opposite extreme of the glider, right? And our mission needs to coordinate those three vehicles, right, within this confined area, okay? So we have this region. We start over here, right? So we'll assume the ship starts in here. We want the ROV, right, to pick up samples in these locations or some subset of these. We want the AUV to visit these targets, right? And without them colliding into each other. There's a set of underwater obstacles the ship doesn't have to worry about, but the ROV and the AUV needs to worry about, right? And then we have a set of surface obstacles which the ship needs to avoid. So each of them has to deal with the different sets of obstacles. Here's an example of a typical mission. So here the ship is going to do this tour, right? It deploys the ROV in orange here, but the ROV is tethered, right? So the ROV is going off and sampling its go regions, right? It then does another deployment where it samples its go regions. Oh no, it's here, and here are the two ROVs sampling. Then the AUV is deployed, and then it goes and visits its targets separately, right? And then goes back to the start point, and then the ship finishes. Okay? So that's an example of a mission we want to generate. One thing to notice is that there are relative position constraints here. So the ROV is tethered to the ship, so it can only work within this range. So in order to control the ROV to go to an area, you have to have the ship follow along with it. Okay? So if you look at the characteristics of the problem, then it involves both activities and paths, right? We deploy the vehicle, right? It moves, we pick up a sample. So both a mix of discrete and continuous. We have obstacles that you've seen. We have coupling between the motions and activities through the state constraints and the dynamics. So the tether range is one example. There's a communication range constraint, right? You can only communicate the surface, but only within some range unless you use a satellite link. There's the AUV battery life. So lots and lots of different dynamic constraints. There are temporal constraints as well, such as the maximum mission length, different periods of time where you need to stay out of certain exclusion regions. And then the planning problem has a long horizon, right? Which is that we have to plan for the vehicle over the day, okay? But we need to respect the vehicle dynamics as well. Okay, so what is the planning problem? So the combined task and motion, or activity, right? The motion planning problem is we need to decide what sequence of activities to perform, and based on Jorg's tutorial, you are now expert in generating sequences of activities, right? We need to decide when to perform them, right? Which is to schedule them, right? And Bob, right, gave you a tutorial, right, on Monday on how to schedule them, right, given a set of simple temporal constraints. So you now know how to schedule, right? And we want to then generate a set of vehicle trajectories, right? And based on Scott's tutorial, you now know how to generate trajectories, right? So we just plug those three tutorials together, and then we're done. Great. And we can go back to our break. Okay, so our goal, right, in terms of the planner is to deal with the coupling between those three things, right? So we want a hybrid task and motion planner for coordinating multiple robot missions, which is what I said before. And then there are two things that drive us. On the one hand, we want to have a sufficient accuracy in the dynamics and the state constraints, right, to generate realistic approximations, right, of the global paths. We're going to look at the problem of planning over the day, but not how do I plan in the moment, but we still need to think about the paths of the vehicles, right? So we need to be able to do this. We know that if we use a classic action representation, which is we discretize the world and we just have preconditions and effects and we don't have time and continuous state, that's just not a reasonable starting point. Okay, or if we have a discrete activity planner, then just call a motion planner, then that's just not going to work. We'll see examples of that later. On the other hand, we want to scale to long horizons. So those two are going to compete together. The way that we can handle longer and longer horizons is to abstract the system more and more and make it simpler, right? But then our dynamics becomes unrealistic, right? We can come up with an approximation of a very nonlinear world, right, by discretizing, right, and having very fine-grained time steps, right, and then linearize the system, for example, right, or simplify the dynamics within each time step. But then we have lots and lots of time steps, and we can't handle very long time horizons. So now we have to somehow figure out the balance between those two competing needs and what's the sweet spot between them. So we spent a lot of time trying to figure out the sweet spot on that, and Scotty is kind of our current take on that. Okay, so the approach that we'll take is that we're going to treat time or particular time steps as being continuous, right? So normally the way that we think about these problems is we don't reason about time continuously, that is, we don't create an analytical function, right? We usually discretize time at some level, and then we only reason at the discrete events, and then between those discrete events, we make it so things aren't that interesting. So for example, in a discrete time formulation, you reason at time t, t plus delta t, t plus 2 delta t, so forth, and then we may have constant control values in those segments, right? And a linear dynamics within those segments, right? But the problem in this case is some things are happening very quickly, right? When, for example, we're actually picking up the sample, and some things are really slow, such as when we're traversing from one place to another. So we don't want to fix our time step. Instead, we want to let the time step vary. So sometimes it can be very long because not that much is going on, and sometimes it can be very short because lots of things are going on. So the first key is to do a continuous time formulation, right? And in fact, a lot of the work in heuristic forward search or PDDL planning, which is folding time into the actions, uses the notion of a continuous time formulation. So we'll be similar to that. The other thing is to be able to have continuous control variables, right? So in a model predictive control, you have discrete time steps, but you have continuous variables. They're real valued variables, so you use an optimization routine to search over that space of possible real valued variables. The other alternative is to discretize those control values, but if you discretize them, then you're really restricting the set of possible control values that you're considering, and then you have a combinatorics. I'll see that in a minute. So now we have a continuous time formulation and a continuous control formulation. We need to be able to encode that coupling, and the way that we'll do that is we'll encode it using what's called a second order cone program, which is a form of convex optimization with very nice properties. The second idea that we would do is that there is a combinatoric part to this problem, and the combinatorics is both in terms of which actions that we pick and how we navigate around the obstacles. The way that we'll deal with that combinatorics is to leverage the insights that we've gotten in heuristic forward search, both in terms of the activity planning, right, which is what you saw in Jorg's tutorial, but also within motion planning, which is what we saw in Sven's tutorial. Okay? So that's the game plan. So that's the way that we're going to solve it. What I want to do is to kind of elaborate just in terms of those key elements of the approach to kind of make sure that you understand that before I then kind of go into the mechanics. So this part in terms of the approach are kind of the takeaways that I want you to have. Okay, so we said that we want to use continuous time, continuous control, and I belabored the point. So it must be important for some reason. So why is it important, or why is it difficult to deal with continuous time and control? So if we write down the dynamics of the system, right, then the dynamics, right, in a linearized dynamics is that if I have the state of the system, x, which is a set of real value control variables at time t, right, and I want to know it at time t plus delta t, then I simply take the control input times the amount of time, I add it to xt, and that gives me the time at t plus delta t in a linearized formulation, right? Now, can you think about if I encode this problem, right, as an optimization problem, right, and I allow mu and delta t to be variables, why I might be concerned? So I say to you, okay, so I want you to solve this optimization problem, but I want to have those as variables.
If your time is changing faster or slower than your control is, you might have a mismatch that doesn't work out. That's what I think. It's just like,
In terms of it's not accurate enough?
yeah, if you discretize time too largely, right, but your control input doesn't match that, then you're going to run into problems.
Okay, so there will be the issue of accuracy. I'm just gonna buy that for right now. I'm gonna say, well, that's okay. But even if I don't have the accuracy problem, then if I just am an optimization person and you've contracted me to design a trajectory, given that I'm gonna have constraints like this, right? Because it becomes nonlinear, exactly, right? And the reason why we're concerned with that is at least, well, and it would be different generationally, right? But we hit a point where we said if you want to solve a propositional satisfiability problem, then around 2000 or so we were happy with that, right? And then about 5 years or so later we said if it's a linear program, then we're happy with that, right? And then after that we said if it's a mixed linear program, then we're okay with that. But we kept using the word linear, 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 right? So what concerns us here is that it's not linear, right? Because we have a quadratic term. Okay, so the past insight was we like linear programs. We can always solve those quickly, right? We like mixed integer linear programs because we can solve them pretty fast, though not as fast, right? It turns out, right? So we need to linearize. Okay, so we linearize either by making u constant or delta t constant, and that's what mainly people have done in the literature. So we can fix delta t and vary mu, and that's what the model predictive control does, right? You just discretize time, right? You linearize your dynamics, right, at each state and each state change, and then you solve a linear program. If you're in a convex region, your dynamics are linear, then it becomes a linear program, right? If you have obstacles to avoid, then you use integer variables to handle that, okay? Okay, but if we want obstacles and we want to have activities, then we're going to have to make discrete choices. In the case of an obstacle, right, to represent an obstacle, you need to stay outside of the obstacle. So you end up saying I either stay to the left of the obstacle, to the right, above, or below. That's a discrete choice, and we add in integer variables into our mixed integer linear programming. And then in our discrete time formulation, we copy all the variables and constraints for every time step. So if we have a very long time horizon, then we have a ton of time steps. We have tons of copies of our variables, and we're kind of worst case exponential in the number of integer variables. We have just too many integer variables here, okay? So the runtime tends to be exponential in the number of time steps, right, and the number of choices that we have to make, okay? And so here's a planner that I'll talk about a little bit later called Columbo, which is kind of like Sulu, but it can actually choose actions as well. And what you'll see is that, in fact, as you extend your mission horizon, then it does start growing exponentially. So in fact, the worst case is at some level being realized, where you will see as kind of a preview is Scotty, for whatever reason, doesn't have that problem, and for the reasons I gave you. Okay, so the other approach is we can fix the control values and then vary delta t. And a number of communities have done that. A lot of the work in the activity planning community, right, where you've extended PDL operators to have continuous effects, will usually discretize, right, the continuous variables. So Colin pop up in that line, right? So Danielle, I don't know if Danielle's here, right? So the King's College group has often discretized the continuous variables, okay? So in this case, what you do is we can think that we have actions which are parameterized by control, right? What we do is we discretize the set of possible control values, and then we copy the actions for each control setting, okay? And then what we can do is we can use the heuristic for search planners to deal with that. What happens in this case is rather than the exponent being in the number of time steps, right, it becomes more exponential in the number of actions, and hence the size of the discretization, right? And so then two different problems occur. One is you still are exponentially growing your state space, right? And we found that greedy heuristic forward search will help you in terms of dealing with that combinatorics, but a greedy search is not an optimal strategy, right? It will be susceptible to falling into local minima. It just depends on the characteristics of the problems. It turns out when you do this discretization for the trajectory optimization, the paths that you get by using a greedy heuristic forward search in our experience tends to be highly suboptimal, right? And then the exponent still starts getting you in this case. So here's an example of a problem where we were just moving our velocity in 2 dimensions. So we have the x and the y direction. We discretize roughly 10 possible control values in the x and the y position. So that would give you about 100. Here we have about 120. So to generate a plan, it takes you about 133 seconds, right? Where we can do better, right? We can do less than a second, okay? And the paths that you get have no guarantee in terms of optimality, where in this case you can get guaranteed optimal paths. Okay, so that's the problem with discretizing time and discretizing state, but if we want to linearize, that's what we want to do, right? So the new insight, right, has been the world has changed so that convex solvers have actually gotten to be quite good, right? And I think you heard some about that yesterday. It is the case that convex solvers have gotten quite good. Mixed integer convex solver are not really ready for prime time, okay? So we don't want to use the trick of encoding things as integer variables, right? But we do want to exploit convexity, okay? So that's what we're going to do here. So we're not going to use the integer variables, right? We'll throw away that trick, but we will go from LP to convex, okay? And then that convexity allows us to express that term, right? And so go ahead, we can do it, okay? The other thing is there are a number of constraints about the world that you really need to be able to express for this stuff to be useful, and those kind of go beyond linear. And the most important one that we saw was that we had a relative constraint between how far the ROV can be from the ship, and that you can express as a norm constraint, right? And convex programs allow us to express norm constraints. Okay, so that's the idea, okay? Now, one of the important things in any of these discrete formulations, right, is that we're looking at a set of events, right? And then what we'll do is we'll assume that not that much interesting is going on between those events, right? In our case, right, and normally what's done is you apply a constant control value, right? And then you apply that, and then the system's behavior evolves. And we'll do that same thing, right? So when we ever apply an action, we'll apply a constant value for some delta t. The net effect of that, right, is our control values, right, are going to be piecewise constant, though the length of these can change, right? And then if you look at the dynamics of that will be linear. So what that means is that we'll have lines moving within convex regions, and then that's convex, and we only have to look at the start and the end point of each of those line segments, okay? So the key here ends up being is it's okay to reason about the start and the end, right, of the application of a control value, right, as long as the dynamics is linearized, right, and that the constraints that we impose are convex, right, or linearized, but we're doing is we're multiplying times a constant rate of change, okay? And so it allows us to take both our position relative to some fixed convex region, only check our position at the endpoint to make sure that we've not collided into the obstacle, and then also for our norm constraints. So our relative position between vehicles, right, we can check those relative constraints, right, because of convexity just at the endpoints. Okay? Otherwise, what we'd do is that we'd have to discretize the system's behavior as it's moving, and then we kind of fall back into the problem that we had before. Okay, so that's how we're going to exploit convexity, but we are going to impose the restriction, right, that we are going to have piecewise constant control values, okay? But every time there's a change in the system, right, we can change those values. Now we then have to deal with the combinatorics, right? So I said we don't have mixed integer convex solvers that are efficient, so we don't want to use the integer variable trick to encode our choices. So in this case, we have two combinatorial choices, right? We choose an action, right, which is what Jorg was talking about, and we decide how to go around the obstacle, okay? And the passive insight, as I said, is we'll frame this as some constraint program or as a mathematical program, and then we use the discrete variables to represent those choices. And those could be finite domain variables, they could be logical variables, or they could be integer variables, but it's the same idea, right? Okay, so for example, if you look at the classic planning problem, which is atomic actions, preconditions, and effects, then one of the first kind of promising planners in terms of performance was something called SAT plan, right, or a variant of that, which used a plan graph to construct its encoding called black box, right? So it would take the planning problem, reformulate it using a plan graph that wasn't relaxed. An unrelaxed plan graph represents mutual exclusion where actions can interfere, right? They would encode into propositional logic and then solve the problem. And that worked a lot better than the state of the art before, but compared to the performance that we're getting today, you just don't think about using a SAT encoding, right? So heuristic forward search in that case works much better than a propositional satisfiability solver, which is basically doing tree search, which is assigning the variables, right? So it's also doing a search, right? But it's doing a search over partial assignments to variables as opposed to going from an initial state. Combing is another planner that we developed, right, which takes the idea in black box, right? So it takes a plan graph, but what it then adds in is the continuous dynamics, right? So there's something called a hybrid flow graph, right, which you can think of it as an extension to the plan graph, right? And then we would re-encode that into an integer linear programming and would use branch and bound. But in both cases, those techniques only scale so far. And I think we showed you this plot I showed you earlier. So if we use a hybrid flow graph, which is basically a plan graph with discrete and continuous variables, and code as a mixed integer linear program, then you start dying because of the exponent. Okay? So the new insight is we'll use, as I've said before, is we're going to use heuristic forward search, right? Both to make a set of choices, right, on actions, which is what we have in activity planning, and avoidance of the obstacles, which is what we have in path planning. Okay? And then we need to define a heuristic for both of these. Now, you could define one heuristic which tries to deal with both, but it turns out that the properties, right, which would help you heuristically to guide yourself in terms of paths are different than the heuristics you use to choose the appropriate activities. So we're going to view these as two different heuristic forward search problems, right? Each of which is going to be leveraging off a convex optimization. So what we'll then do is we'll take this heuristic forward search algorithm, we'll hybridize it, right, with a convex solver. So we'll have a master, right, which is doing a combinatorial search, and then a sub-solver, which is solving a convex problem, and solving a convex path planning problem, right? So we have an activity planner, right, which we can think of as taking what Jorg talked about and extend those ideas, taking this into some planners like Colin, Optic, and then into Scotty. And then we'll take the notion of a qualitative state planner, which is we've generated a plan, it's going to constrain the state of the world. We need to come up with a motion planner which can execute that plan. So a qualitative state planner can generate a trajectory which satisfies the constraints of that plan. But rather than using Sulu, I'm going to use convex optimization to give you a different implementation of a qualitative state planner. Okay? Now, one way that people typically deal with combined activity and motion planning is that you call an activity planner and you talk to the AI planning community and say, give me a black box activity planner. It generates an activity plan, right? You then go into ROS, you then generate a motion, right, for the next activity, and then you hope that works out well, and that's fairly optimal. In some cases, that works pretty well, right? But there are many cases where the activity and the motion planning coupled together quite well. So I'm going to give you an example, right? So my collaborator at Hui, Rich Camilli, right, does maybe a half a dozen or so, right, expeditions a year, and they always have these really interesting anecdotes. So in this case, they were doing one where usually a ship has a remotely operated vehicle, and in the Deep Submergence Lab, which is a national facility, their ROV is called Jason, right? It has a manipulator, right? It's teleoperated, right? And it has one AUV called Sentry. So normally a mission involves you deploy Sentry, and you kind of say go off and do your thing, and then you maintain the ROV, and then you kind of go back and get the AUV. So they sent off Sentry to do its science, right? They then start running Jason, right, to do its ROV operations. Sentry kind of goes away, it comes back nearby, right? Supposed to stop so they can go pick up Sentry. Sentry comes by and it doesn't stop. It's at the end of its mission. For some reason, it didn't execute the last command, which was to stop, and it just keeps on going. So suddenly, Sentry is going away, right, from the ship. Now, it's also headed towards a shipping lane, right, which is bad news. You don't want an AUV in a shipping lane colliding with the ships. So they need to go get Sentry. So they say, okay, what's the simplest activity plan? So minimize the number of actions that you perform, right? Simplest action is full speed ahead, go get Sentry. So they start going to Sentry with the ROV tethered and dragging behind it. And they can't go as fast as Sentry. So Sentry just keeps getting further and further away and getting closer and closer to the shipping lane. So they then had to decide, which is a very stressful situation, is let's stop, right? Which is Sentry's getting further and further away and closer to the shipping lane. Let's pick up the ROV. I don't even know how long that takes to do. They get the ROV on board, and then they chase after Sentry, and then they find Sentry, right? And happy story, they get Sentry before it gets into the shipping lane, right? And they stop it, right? So that was a more complicated plan, but it was the more optimal, in this case, the only feasible plan, right? So in those cases, we can't just minimize the number of activities, right? We need to have an objective function, but the objective function in this case is in terms of velocities in the paths. So we need to reason about the paths when we decide the activity plan. Okay, so we do need to think about that as a coupled problem. Okay? So the activity planner does need to think realistically about the motions. Okay? And the way that we'll do this is we'll have a path planner, right, which can reason about dynamics. And I've kind of talked about how we're trying to find the sweet spot in terms of those paths, right? And then in our heuristic, when we evaluate an activity plan, we will call this quantitative state plan path planner, but we want to do it quickly, so we'll solve a relaxation of the QSP planning problem. And our relaxation, in fact, will be ignoring the obstacles, right? Which is the combinatorial part. Okay, so that's the approach, okay? So let me kind of give you the problem statement just so that you know what the problem is, followed by the solution. Some of the problem state is motivated by the solution, but I'm just going to give you the bottom line in terms of the problem statement. So we're going to start with a PDO-like description. We're expressing some things that you can't in the kind of the standard formulation of PDO, so we have some augmentations, and we'll refer to that as PDO Scotty, right? But it stays with PDO as much as it can. So we have a set of initial conditions, which are going to be assigned. So we'll have a state space, which is a set of continuous variables, a set of discrete propositions, right? The initial conditions will be either assignments to those discrete and continuous variables or constraints on the discrete and continuous variables, right? We have a set of goals, and those goals will, today it's just we have an end goal, there's a temporal constraint on when that's achieved, and then there's some constraints in the end goal in terms of the discrete and continuous variables. So we want the AUV to take images in a region A, we want the RLV to sample in B and C, and then we want the AUV, the RLV, and the ship to end in a destination region. Okay? The actions that we'll have, there's actions that the ship can do, the ROV can do, and the AUV can do. So the ship can navigate. With respect to AUV, we can deploy it, which the ship has to be involved in. The AUV can navigate, and it can take images. The ROV, we can also deploy and navigate. We can recover it, right? And then we can sample regions as well. Okay? Our environment will be a set of convex obstacles that the vehicle either needs to avoid or convex regions that it needs to stay within. So it's a combination of those, and that allows us to express what we saw here. Scotty then generates a path, which is kind of what we saw before. So the plan is a sequence of activities. It'll be a schedule of those activities. It'll be a set of control trajectories, which I've said is piecewise constant, and then a set of state trajectories, which I've said are piecewise linear. Okay? Now, what will be important is our action representation and what can you express in terms of the action representation. So that's the remaining thing I need to describe. So we'll have actions which have some duration. So they have a start and an end time, right? And will have some conditions which are true at the beginning and the end, but throughout. So we'll have a duration, and we'll express that as a simple temporal constraint. We have a set of conditions on discrete variables, right? And those conditions will be at the beginning, right, is what you've seen so far, but they can also be true throughout the duration. So we want to maintain some condition. Okay, so we'll have conditions at the start, throughout the duration overall, and at the end. And then the effects, likewise, can occur at the end, and they can add or delete conditions, but they can also be true at the start as well. Okay, but we then add in the continuous variables. So we do have a set of continuous variables, and it's similar in terms of conditions and effects. So they're at the start, overall, and the end, right? So here's an example of a continuous variable in terms of position, and we have a relative constraint between the ROV and the ship. We've said that the ROV has to stay within the radius, right, of the ship, defined by the length of the tether. Okay, and then we have a set of effects, and we not only affect discrete propositions, but we can affect continuous state variables. Okay? Right, and then that's what governs the movement of the state of the vehicles. Okay, so let's just look at the continuous part of this a little bit more, right? So I said that we have a set of control variables which are subject to constraints, and they influence the state of the system. So they influence the continuous state variables. The continuous effects, we will restrict them to be first order dynamics, right? And so those will be a linear combination of control variables, right? So here's a simple case where we only have one influence to the state, right? Which is that we adjust the velocity. But in more general, right, it can be a sum of constant control variable influences. Okay, so then we can aggregate, both the currents, for example, right, and the propeller, and those two influences on the vehicle, right? So that'll be important. And then we also have norm constraints, and we saw the radius as one example of a norm constraint. Things like battery consumption, right? In this case, what we're doing is we're expressing expressing the battery level as a function of velocity. We consume more energy as the velocity increases, but it's not a linear relationship. It's a quadratic relationship. So through convex optimization, we can express those constraints as well. Okay? And then it just kind of elaborates the constraints in general. So the conditions, right, are simply linear inequalities and inequalities, right, plus convex quadratic state constraints. Okay? Okay? So, for example, you can maintain yourself to be in an ellipsoidal region, and you can maintain the distance of two robots. So this just kind of pulls it all together. So this is just kind of going back to our example, right? So in this case, we can represent these because they're convex regions, right? Right? The places that we're going, again, we can express as convex regions. We can express the duration of our total mission as a simple temporal constraint, which is just two linear inequalities. So we're happy with simple temporal constraints. We can constrain the duration of the individual activities, so the actions are durative. We can represent a simple first order dynamic. So for each action, we can change the dynamics, right? But as we change the control modes, the dynamics can change. But we're going to assume that within each control mode, right, that we have a linear dynamic. Okay? And then we can also represent battery draw, which is in these vehicles. Reasoning about how to maximize the energy efficiency will be important. Okay? Now, if we took that problem and I was going to do a straightforward formulation as an optimization problem, right, then this would be both mixed integer and non-convex, and I've already said that that would be problematic, right? Or if you look at those kinds of activity planners which use an LP, right, to check constraints, right, then you won't be able to express these problems. Okay? Okay. Now, if you look at the output, right, then I've already kind of said what the output is, but let me just kind of, for completeness, show you then the output. So we were given an initial condition, a goal set of states, and then a bound on the duration of those activities, and we're given an objective function for it. The output is then a sequence of actions. We can have concurrent actions, right? But what we're going to do is we're going to reason about the beginning and the end of those actions. So we'll have a plan which is a sequence of actions for each of those vehicles, and then some precedence ordering of when the start and the end times of those actions, plus some additional temporal constraints on the duration of those activities, right, which again are simple temporal constraints. In addition to this activity plan, right, we'll generate a motion plan and a control trajectory. And so this is just an example of a plan that Scotty generated, where in this case, the ship moves to a location, it deploys the ROV, remains static until the ROV does its mission, and then it goes back and picks it up. Okay? So that's the problem. Okay, now I just need to tell you how we construct a planner which can do this, right? So what I'm going to do is I'm going to particularly talk about the path planning component, and then I'll talk lightly about the activity planning component. If I have time, then I'll talk about how do we fold this within a receding or rising framework, which is work that Marlise is working on, but we'll see whether or not I have time to do that or not. So since you worked with Sulu, right, I thought it would be useful to kind of remind you actually what it's doing, and because it's doing something very similar to model predictive control, but it takes the notion of an activity plan and it tries to achieve that plan. So let me just kind of review that a little bit. So when I've constructed an activity plan, right, not only does it say what actions I need to do, but it imposes constraints on the state of the system and on the duration of the system. So here's an example of an activity plan, right? And when first Sulu was developed, the activity planner was a planner called LPG, which was a heuristic forward search derivative planner. So LPG would generate the activity plan. And then we said, okay, well, we need to actually control the vehicles. We'll go to the control community, right, and say, do you have anything that could execute this plan? And they said, well, we have model predictive control. And I say, can I give it the constraints of the plan? And they said, no, just tell me an endpoint to reach. So they didn't have an ability to take the constraints that the activity plan had developed. So the question which kind of led to Sulu was, how do we develop a model predictive controller which can take the constraints of an activity plan? Okay? And the constraints is what we're calling a qualitative state plan, right? And then Sulu is a model predictive controller for that. So here we have a plan which was We want to remain in the bloom region, right? We then want to be in a mapping region, and then we want to be picked up. I've kind of abstracted away the discrete parts of the change, only the constraints in the continuous state. We have a set of start and end times and temporal constraints on the start and end times. Each of these activities are constraining the state of the system. It's either constrained to be in some region or outside of some region, okay? So the activities have been replaced with state constraints, but we otherwise have, and we have temporal constraints on the duration of those activities. We'll refer to those activities as episodes in the literature, okay? So it does mean that the activities are coupled between time and state constraints. You can think of it as a form of moving obstacle problem. Each episode is producing or removing an obstacle, okay? So we can solve this, right, online using a mixed integer logic or integer linear programming formulation, and that's what Sulu does, and you saw Sulu work, and we use Sulu quite a bit in controlling the glider, and it works actually quite effectively. The horizons are short enough, right? Maybe it goes off for about 8 hours, and the discrete fixed time step formulation allows us to accurately model the dynamics. A second approach is if you have to respond really quickly, then you can pre-compute a set of policies. So we have another qualitative state planner called Chekov, right, which is much faster in its response, and I'll kind of briefly show you an example of that. And then central to Scotty is a third kind of QSP planner, which can handle long horizons. So what do we know? So what we know is that we can generate a path by viewing that as a trajectory optimization problem. So we'll have some objective function, right? We'll have some variables which define the path, right? So we'll have an objective function over the path, right? And then we'll have some constraints on where of the feasible region for that path, right? For example, your configuration space, and I've folded the constraints which define the paths such as the dynamics, I've hidden it within this statement here. So always the problem ends up being is how do we encode that problem? In our case is how do we encode a trajectory optimization problem which includes the constraints of the qualitative state plan? So that's really what I want to talk about here. Now, if I was going to frame trajectory optimization as a mathematical programming, then this is kind of what the standard formulation looks like. What I would do is I'll discretize time with some time step, and so then I'll have times 1, 2, 3, 4, 5. The difference between time 1 and 2 is I add delta t at each step. Okay, so if I want to formulate the problem, then I'll have the dynamical constraints. Okay, so I have a set of dynamical constraints. I'll have a set of spatial constraints, such as stay within some region. I'll have an initial state condition, a go condition, right? And then I'll have some constraints on my actuation. What are my values of my control variables? And then what I just do is I discretize time, and I replicate all my variables for every time step, and then I just replicate my constraints for every time step. I give it to a mathematical programming solver, and I ask it to solve it. Okay, and that's what Sulu is doing, and that's what most model predictive control frameworks will be doing. That's what Scott talked about. Okay? And this is just an example of taking, for example, a convex region I want to stay in, and I can represent that by a conjunction of linear constraints, by turning this region into a polygon, introducing a constraint for each of these boundaries. Okay? If I'm trying to stay outside of an obstacle, then this says I want to stay inside each of these half planes. If it was an obstacle, then I want to say that I want to stay outside of one of those. So this and becomes an or, and that's where I'll become unhappy, right? But I can use integer variables for doing that. The problem that Sulu has to solve is I now have a qualitative state plan, and I need to encode the constraints of the QSP in the trajectory optimization. So in this case, there are really three things that I want to do. Either I want some activity where I want to start in some region, or I want to end in some region, or I want to remain in some region. Now that region may be actually I want to stay outside, right? But I really want to talk about how can I encode start, end, and remain, plus the temporal constraints. So if we want to encode the temporal constraints, then those are easy, right? If I want to say that the duration is within this interval, I just represent that by a lower bound constraint and upper bound constraint. So what I do is for every activity or episode, right, in my qualitative state plan, I introduce a variable for the start time and the end time, right? And then I add in two linear inequalities to capture the simple temporal constraints. Okay? So that's quite easy, right? Now let's take the remain in activity. So I'll have some region. I'll represent that region by a set of linear inequalities, right? That I need to maintain or avoid. And then what I want to do is to say I want to remain in from ES to EE. So what I do is, for my current time step, I say, is my current time step between the start and the end of that episode? If so, then I need to remain in that region, right? So this is just simply saying, if the current time step, which is a constant, right, is between these two things, which are variables, right, then enforce this constraint. And I can fake out, I can encode propositional logic or implication using mixed integer variables. And I'm not going to tell you that. You can just figure that. You can look in the literature. Okay? But that is the part where I have to make a choice. So that is combinatorial. Okay? And then I'll just take one more example. So if I take end in, right, then I want to end, right? So I want to be in region R at E of E, because, and the end event I've treated as a real valued variable with respect to scheduling. But then with respect to the state constraints, I've discretized time, right? So what I will say is, if the current discrete time is within half of a time step of the end, then I'll enforce this constraint, okay? And then I can just get start by a combination of end and remain. Okay? So given that those kind of encoding tricks, then I just take a QSP, right? I take my obstacles in dynamics, I get a mixed integer linear program, I solve that optimization problem, and that's in fact what Piecewise is doing, right? And this is just an early example of Piecewise doing some path planning to execute the activity plan that LPG generated. Within the model predictive control framework, what it's doing is it's solving the planning problem over a short time horizon, and then as soon as it generates a new trajectory, it starts executing it, estimates its state, and it just keeps replanning, right? And that's a standard model predictive control framework. Okay, now, let me just kind of mention, so in terms of understanding this space, right, is there are systems for which doing a model predictive control doesn't respond fast enough, right? And the example in particular is if I'm walking, right, then the thing is, if I'm walking is a linearization doesn't work that great. There's ways to kind of get around that, right? But if I'm walking, right, and I trip, right, then I can't call some convex solver, right, to generate a new trajectory. By the time I would get a solution back, I would have fallen on my face, right? So in those cases, what I want to be able to do is to pre-compute the set of possible paths, right? So that's the one insight. The second insight is for example, if I'm falling, right, so I trip and I start to fall, right, then my center of gravity has a lot of inertia, so I'm going to move really quickly. So I'm not going to try to change the movement of my body. What I'll do is I'll change my feet, right? So I speed up my feet to try to get under my body, right? That's actually a scheduling problem. That's deciding the arrival time of putting the feet down. And Bob talked a lot about scheduling. So he talked about, and particularly about dynamic scheduling, right, where it was scheduling to respond to disturbance. So that was the notion of dynamic controllability, but it was pre-computing a set of possible policies. So scheduling was almost lookup. In this case, you want to do the same thing. So you want to schedule your feet, but you have to schedule your motions as well. So the reason I'm kind of highlighting this is it kind of couples what you learned with Bob, right, in terms of dynamic temporal reasoning by pre-compilation and then coupling that into the continuous state as well. So here's an example where we're walking. So the qualitative state plan just simply says right foot, left foot, right foot, left foot, heel strike, toe off, right? So it's a qualitative state plan like we had before. Here's an execution of that qualitative state plan, right? So it's walking, so it's no longer statically stable, it's only dynamically stable, right? And if we disturb it, it rejects the disturbance very quickly. In order to do that, it just kind of generalizes this dynamic execution strategy. So remember, just to review what Bob talked about, is to adapt to temporal uncertainty, what we do is we will assign activities just before we perform them. In this case, what I'm going to do is to assign when I reach my goal, which is the time that I want my heel to strike or to do toe off, right? So I'm going to schedule the end goal of the activity as the end of the activity as opposed to the start of the activity, right? But I'll do that in light of the temporal uncertainty, right? And so I'll do that just before executing. I'll then reduce the latency of scheduling. This is what Bob did, right? Was by compiling the temporal constraints into something called a dispatchable form, right? So it made the implicit constraints explicit, and that was the work by Mushatala, Paul Morris, and Simerdinos. We're going to do the same, and then what you do is you keep updating your policy incrementally as events are scheduled, right? Which you'll just see reflected here. in that propagation. What we're just going to do is that we're going to introduce the continuous variables as well. So we're going to reduce latency by pre-computing out the set of possible trajectories as well as the possible schedules, and we'll refer to that as a flow tube, and that's just a bundle of trajectories which all reach the same target goal region. Okay? And so we'll introduce this notion of a flow tube. So if I want to reach some region, right, then these are all trajectories which will reach that region, and I'll pre-compute that using a reach set analysis, which is techniques from model checking that Dan will be talking about model checking kind of shortly. Then what I do is once I compute the flow tube, then I will also compute the temporal constraints which are implied, which is basically given that flow tube, then how soon or how late can I arrive at the region. Those give me some temporal constraints, and then I'll fold that to the dispatchable algorithms that Bob gave. Right, so the net effect is what it will do is it will schedule when to try to achieve each episode or what each arrival time is, right, based on the actuation constraints which are captured in the flow tube. Once it's scheduled, then it'll just follow the flow tube, right? If I disturb my behavior, then I'm in the flow tube and I get disturbed, right? Then I just follow a different line along the flow tube. If I get disturbed and push myself out of the flow tube, then I reschedule the arrival time so I'm within the flow tube. Okay, so just to finish it, I can take the qualitative state plan. I do a backward reachability from these regions in the state plan to construct the flow tubes. I can either use a simple linearized kind of inner approximation, or I can pay the cost of doing a more detailed representation of flow tube, and then I use the flow tube to do the execution. But it's really this notion of dynamic execution extended. Okay, so let's just give you a notion of qualitative state plans and then the different things that you can do to be able to execute them efficiently. In our case, it's not the issue of efficiency. The issue would be that I want to be able to plan over very long horizons. So that's what I'm going to focus on now. So given the constraints that I gave you in the Scotty planning problem, right, and the PDL representation, then I'm going to talk about how to plan a path which satisfies those state and temporal constraints for multiple vehicles. And I'll first look at the no obstacle problem, so I don't have to worry about how to get around the obstacles, and then I'll fold in the obstacles. Okay? So this is just a review of what we had before, right? So in this case, I had an initial problem, right? The Scotty activity planner, which is a heuristic for search planner, which we'll treat at the moment as a black box, will somehow construct to me an activity plan, right? And that activity plan has a set of actions and constraints on time and this continuous state variables, so we can think of that as a qualitative state plan, right? Scotty path, right, will then output a control in a straight trajectory, right, which satisfies the qualitative state plan under the dynamical constraint. So we're not going to discretize time. We're going to allow time to be variable, right, but otherwise it's like SU. Okay? So again, we said the way that we'll do this is we're going to encode the trajectory optimization problem as a second order cone program, right? So in order to do that encoding, we'll first introduce for every start and end event a decision variable, the same thing that we did for Sulu, right? So we'll have decision variables, which are the event times, and then we'll have state variables at each of those events. So we still at every event, so every start and end, will copy our variables, but we won't just do that at arbitrary fixed discretizations, right? And then we'll introduce control variables at each event as well. Now, what is an event? So every time some activity begins or some activity ends, right? These activities are overlapping. We'll consider each of those to be an event. And then when we start adding in obstacles, what we'll do is there's certain kind of qualitative points where we've transitioned around the obstacle. Each of those will be an event as well. So we will copy our variables at each of those interesting events, okay? But all these things are continuous, so we don't have any combinatorial, so we're not mixed integer or mixed logic, okay? And the constraints will be the activity durations, it'll be the state constraints, right? And then it'll be the dynamical constraints. So I just encode those, okay? So most of that is kind of like the encodings that I showed you before, right? But again, we said the straightforward formulation is not convex. And the problem is actually this nasty, this seemingly simple dynamic constraint is problematic, right? So before what I showed is it's C2 times delta T. It's actually C2, but we've represented events. So it's C2 times the difference of two events, right? and that's the next state is constrained to be equal to that. That is not a convex constraint, right? So we can't take the product of two quadratics and preserve convexity. So the way that Scotty deals with this, right, is to say we don't actually need all those variables to be represented explicitly. So we just want to represent that term. So what we're going to do is we're introduce a variable which represents that term. So it's going to be a proxy variable, right? And that's the decision variable that we need to set, is we need to decide that product, which is really what we're going to do is our decision is going to be how long to do. Our decision is going to be how much to change our state value, okay? And so that variable is just, that's a single variable denoted C sub x delta t, okay? So we introduce that proxy decision variable, and then we impose our constraints on that proxy decision variable, right? Which are linear inequality constraints, right? So we can take the difference of time. So in this case, if I have some actuation constraints on the control variable, right, then what I've done is I replaced the control variable with this proxy variable. So my actuation constraints have to be reformulated. So what I just do is I take the upper and lower bound of the constraints, multiply it, of the control variable, I multiply it by the time, and that gives me a new actuation constraint on the proxy variable. And then my state evolution is now linear, okay? Okay, so that's the first thing, right? So that is now how we can encode the dynamics. The second thing for this thing to be realistic is we needed to be able to talk about relative constraints between vehicles for this to be at all useful, and the ability to express norm constraints give us that, okay? So you can look at the papers to see more of the details of the encoding, but the net effect is that our encoding, right, will give us a convex program. We can use the same tricks, right, to encode the QSP, and we don't have to introduce integer variables, right, as long as we remain in convex regions and we know the order in which events occur. So in this case, the qualitative state plan actually has a total ordering on start and end times. And it turns out that the Scotty activity planner generates that total ordering. So in those cases, we don't have to introduce integer variables. Okay? Okay, so that's how we deal with the case where we have no obstacles. Now the question is, how do we deal with obstacles? Okay? So what we had learned before, I guess I didn't kind of show you a slide on it, right? But the classic approach, right, to represent an obstacle, right, is we say, we represent the convex region by, say, linear inequality constraints, and then we say that if we preserved all these linear inequality constraints, then we would be in the region, but we don't want to stay outside of that region. So at least one of those linear inequality constraints has to not hold, right? So what we do is we flip them, right? So we say, stay on the other side of the line, and we say we have to stay on the other side of one of the lines which define the polygon, and that makes sure that we're outside. So we say we want to stay out, we want to stay outside here, so we want to satisfy this linear inequality constraint, or this one, or this one. Linear programs like ands, but they don't like ors. You can introduce ors. That's called a disjunctive linear program, right? And Ballas kind of introduced the notion of disjunctive linear programs back in the 60s, but his solution was to say we won't represent or. What we'll do is we'll introduce binary variables, and then that was the introduction of binary integer programming, right? So to represent avoiding the obstacles, we need to say stay outside of the line, right? And that involves encoding an or, and then we have to choose amongst the or. We don't want to do that, right? And I kind of showed you the exponential growth that we get when we add in those integer variables. So what we do want to do is what we will do is we want to restrict the robot to remain inside a convex region or a sequence of convex regions. So if we have a set of overlapping convex regions and we need to stay in them at any point in time, then our path is in fact convex. So the approach that Scotty takes, and it kind of leverages off the insights from Dietz and Tedrick, right, is rather than thinking about the obstacles, what we're going to do is we're going to think about the duals, right? So given a set of obstacles, right, then what Scotty does is use the algorithms, the same ones that Dietz and Tedrick use, to generate a tiling of overlapping convex regions, so not tiling, but a covering, right, of the free space through a set of convex regions, okay? And that's what we have here, right? So our space will be a set of overlapping convex regions. And then what we want to do is we want to find a path through a sequence of convex regions which take us from the initial state to the goal. And because our line is contiguous, that sequence of convex regions needs to be overlapping, okay? So Scotty works as follows, right? So it's given now a initial environment which has a set of obstacles plus regions that we want to be in, right? So we now have surface obstacles, right? This is the plan that the Scotty path without obstacles would generate, right? But what we want is to generate a path, right, which avoids the obstacles. So we take the qualitative state plan, we take the set of obstacles, right? We generate the set of safe regions, right, from the obstacles, and then the Scotty path, right, generates a solution, right, which is the obstacle-free path. So how does it do it? So given the safe regions, right, and the QSP, it's going to abstract the safe regions to what's called a connection graph, right? So the connectivity graph will basically introduce vertices for every point at which a set of regions overlap. And there's two ways that you can formulate it. But basically what the graph will represent is the set of convex regions, right? And then whenever they overlap, a line that moves between those convex regions. And then in order to identify a sequence of convex regions that take us from the initial state to the goal, we'll identify the region containing our initial state, the region containing our goal state, and then we'll find a path in the connectivity graph, and that gives us a sequence of overlapping convex regions. Once we have that, you can use the encoding that I gave you before to find a trajectory through those regions. And because they're convex, I just keep adding them in. Okay? That makes sense? Okay, so the problem then ends up being one of, given the connectivity graph, I need to identify a sequence of regions. Okay, so I'll refer to that as a region assignment. And you see that here. So here's our activity plan, and it's kind of shown here, right? And then between every pair of events, I have a sequence of regions that I move in to satisfy the state constraints at each of those. So my problem is find the region sequence to get to the first event, then the second event, and the third event, and so forth. Okay? And the way that I'm going to do that is I'm going to do that using a heuristic forward search. Once I generate that sequence, I can construct a trajectory. Okay? In order to do a heuristic forward search, I need to have an informed heuristic. So I'm also going to use a path planner or a relaxed version of the path planner to compute the heuristic value as I'm exploring the set of possible regions. So what I'm going to do is I'm just going to focus on explaining or illustrating the process of the region assignment and how heuristic forward search is done there. So if I was to use a naive approach, then what I would say is I would just take the connectivity graph and I would say what's the shortest path in the graph. I could say that every edge has one cost, a cost of one. That would give me the minimal set of convex regions to go through, but that's meaningless, right? Some regions take a lot of time to go through. Some of those regions take no time at all. So I don't want, what I need to do is to figure out the sequence of regions which produce the optimal trajectory, and that corresponds roughly is to be able to attribute an edge weight, right, to the movement between convex regions or moving in them. Okay? So this is just an example where moving between two large regions, right, could actually take me a lot more time than going through a small set of convex regions. Okay? So to find this optimal sequence, right, I need to be able to kind of estimate the edge weight. So you can think of it as a weighted graph. I have to estimate those edges, and then I don't know them in the future, so I'll use A star for that. Okay? So here's just an example of it. So I start in my initial state. I set the goal to reach E1, right? And then I begin to identify a sequence of regions from the start to E1. Okay? So I have a set of candidate regions, right? I'm going to need to evaluate the heuristic value for each of those, right? So I'm going to need to be able to estimate what's the cost to get through that the regions I've committed to so far, plus the cost to go. The cost to go, it'll be a relaxation where I'll ignore the rest of the obstacles for the cost to go. Then what I'll do is I'll compute both the cost that I've had so far and the cost to go, because those two paths couple, right, by framing a problem to the Scotty convex path that I gave you. And it will find a path that goes to the regions I'm committed to, and then the remaining region while ignoring the obstacles. And so solving that Scotty path problem will give me F, which is G plus H. I also have to have an end test, which is how I arrive at my goal, right? So the result of the path planner is it's going to try to minimize the distance to the goal, and when that goal is 0, then that's my end test. okay? So then I just keep doing this expansion. So what you'll see on the right is just how the path keeps improving, right? And so you'll see that more and more of the obstacles are taken into consideration. Once I've reached my event, right, then I have a new event and a new goal, and then I just kind of repeat that process, okay? Until all my events are connected through a set of regions. So the net effect is not only do I have a set of activities which start and end, and those are engaging dynamics, right, and state constraints, I also have a set of regions that I'm going to be in during that period of time, so then that constrains me to be within some convex region for that period, okay? But then in computing my heuristic, then I have an obstacle-free heuristic to evaluate, and then when I have an end plan, then I am obstacle-free, okay? So I'll have an exact path. So that's how Scotty with a set of obstacles works, right? So we have both the convex and the non-convex, right? The non-convex, or the one with obstacles, use the obstacle-free method as a subroutine, okay? So here I just want to show you a few different examples, right? I'll just kind of go through them quickly. So in these cases, right, what we'll do is we'll minimize, right, the distance travel and the total time in the mission, right, as a weighted combination of the two in each of these cases. The first example is we have a ship, right, which is deploying an ROV, right? So we deploy the ROV, we visit A, we visit B, and then we recover the ROV. Here you see the ship moves close between A and B, it then deploys the ROV goes to A and B, right, and then it picks up. Okay, so kind of the example that we saw before. In the second example, I'm going to remove the constraint that the ship can't move. So before I had actually imposed a constraint that while the ROV is out, the ship remains constant. So now I'm going to say that the ship can move along with the ROV, and we can see how the plan looks different in this case. Right, so here we see the ROV, right, goes to A, the ship is moving along, right? So it's allowing the ROV to be more mobile, but the ship is making sure that the tether doesn't break, okay? Here's an example of a multi-vehicle rendezvous where each vehicle has different velocity constraints, hence the faster vehicles have to kind of help out the slower vehicle. Right? So then they find the sweet spot of where to come together. And it's both the velocity of those vehicles and it's the obstacles that they're dealing with that it has to balance out. So it does a pretty effective job at that. Here's an example of a two-vehicle mission with a lot of obstacles that's just starting to talk about that is kind of pushing the scalability of the algorithm. So in this case, they need to move together, right, in a convoy for a while, so to speak, and then they kind of go out. Here's an example that often within the AUV missions, communication is a real problem, right? So you can't communicate underwater. What you do is you go to the surface to communicate, right? If you're far from the ship, right, then what you do is you do a satellite link, right? But that becomes really expensive. So what you really want to be able to do is to have surface vehicles which can act as communication relays, or you use acoustic modems and you have communication relays under the sea. So for them, it's really important to be able to manage that communication relay effectively, and that's what you'll see here. So the vehicles are doing their mission, but the vehicle which is acting as a communication relay is staying in the position which allows the two vehicles to have as much flexibility as possible. And then I have to kind of go give you the road example before, because I gave you that as a motivating example. So this is just the rogue example, right, where you will see in the end that the optimal plan ended up going over to the ROV, picking the ROV, which was the green little line, right, and then once it picked up, then the vehicle was moving much faster, and then it intersects with Sentry, and we have the happy Hollywood ending. Okay, so that's Scotty path, right? So in my remaining time, right, then I'm going to talk about the activity planner, and I'm going to leverage off the fact that Jorg has done a beautiful job of explaining to you heuristic for searches and for hill climbing and the relaxed plan graph. So I just will leverage off of those ideas, right? I'm actually going to slip through a few slides quickly, which are the ones on Kongming. The only thing that I'll note in Kongming is that Kongming, right, is an example of a planner which had a continuous dynamics and used an extension of the plan graph. The way that it extended the plan graph, right, is that with each fact layer, it has a set of discrete and continuous variables For the continuous variables, it would have a set of linear inequality constraints, constraining the region that those could be in. When you talk about reachability from one fact layer to the next, we'd represent that by a flow tube, right? In this case, that flow tube was represented within the constraints of a set of polygonal regions, so it was using a linear approximation, which is also what we'll be doing which Scotty, Colin, Optic, a lot of the hybrid planners do with, is they use that kind of approximation of the evolution of the dynamics, and what they do is they do a linear bounding approximation. In this case, what we'll do is, because we're relaxing kind of we're representing the set of possible plans, but some of those may be infeasible, what we'll do is we'll have an outer approximation of the dynamics, right? So the tube is a linear outer approximation of the trajectories that the system could go through. And that's what's referred to as a hybrid flow graph. You then need to add in the temporal constraints, which is referred to as a temporal relaxed plan graph, or temporal plan graph. If you take the idea of a hybrid flow graph plus a temporal plan graph, and then you do a relaxation, then you get a generalization of the relaxed plan graph that Jorg was talking about. In the case where you're adding continuous dynamics, then when you had discrete variables, a plan graph would represent the fact that you have add and delete effects and they can interfere, where the relaxed plan graph doesn't worry about delete effects. If you want to encode the interaction between the addition and deletion of actions, and they're called mutual exclusions, in the hybrid flow graph, those correspond to a constraint, which is that the set of trajectories or the tubes need to have a non-empty intersection. So that's the idea in the hybrid flow graph. And so just like what Jorg has done is taken a plan graph and relaxed it to construct the relaxed plan graph, we'll take what you can think of as the hybrid flow graph and then compute a relaxation of that as well, right? Now, in those cases, right, so I'm just going to skip over that. Okay, and it controlled vehicles, but not as well as we can today. Okay, so let's talk about how Scotty does the activity planning, okay? So we're going to have a heuristic forward search planner where the heuristic is going to be solving a QSP path planning problem, which is what I've already given to you, right? So here's just a reminder of the example that I had before. So in this case, I have the input that I had before, which is goal, initial conditions, and now a set of actions, right? And I kind of gave you the description of the action models where they have discrete and continuous variables, right? They have discrete and continuous effects, and they have conditions on discrete and continuous variables. So that'll hold here as well, right? I then generate a plan, and what I care about, that Scotty activity cares about, is it generates a sequence of activities. So it decides what activities to perform in the order in which they start and end, and then it imposes an additional set of state and temporal constraints, right? And then in the end, it'll generate a schedule and control trajectory and state trajectory, but we already know that the QSP planner is going to be responsible for those three. Scotty activity just needs to come up with the action sequence for which we can generate a feasible execution. So we're going to do this by heuristic forward search. So we're going to do heuristic forward search using plan graph, and we're going to do a relaxation, right? So, and we'll do this by basically adding in the flow tubes using a linearized dynamics, okay? So we'll extend the relaxed plan graph to include continuous time, right? Continuous state and the dynamics, right? And that encoding is inspired, as I said, by ideas in terms of encoding, in terms of both the temporally relaxed plan graph and the hybrid flow graph, and is inspired by a whole family of planners, only a subset, which I've probably done a fair job of acknowledging here, including LPGP, metric FF, Column PopF, and optic. Okay, so the first idea that we leverage, and it was really, at least the first time I saw it, was in a planner called LPGP by Fox and Long, right? Was if I have an action which has duration, right, then the way that I'll deal with duration is I know how to deal with actions which are atomic, right? They have some preconditions, they have some effects, and they occur instantaneously. So I can leverage all those techniques, right, if I take a derivative activity and represent it by two actions, the beginning and the end, okay? So for every derivative action, right, LPGP, Colin, all these planners will introduce a pair of actions referred to as snap actions, right? The conditions at the start, the duration at the end will be encoded as preconditions and effects of those snap actions, right? And then we'll add in some additional constraints which enforce the time, Okay? So Scotty, like all its precursors, will divide activities into start and end snap actions, right? So then when you're doing heuristic forward search, it's going to be planning, but it's just going to be planning over the snap actions, okay? So it generates an ordered sequence of events that achieve the goal, where the events correspond to the invocation of a snap action. And so that's just what's going on here, okay? So in this case, it decides not to navigate, it decides to start to navigate, and it commits to it's going to start to navigate next. In this case, it identifies a set of applicable snap actions. Here's an action that it rules out as inapplicable because its state constraints are not satisfied, right? And then it does the expansion, okay? The heuristic in this case will be the number of activities to reach the goal. Now in this case, it's not the number of snap actions, right? It's the number of activities, right? So it needs to evaluate the number of activities which correspond to the snap actions that it has. And then within the relaxed plan graph, when it evaluates the number of actions, it has to compute the number of activities, not snap actions, or derivative activities, okay? It then needs to test the consistency of the partial plan, right, at each point, right? So here's an example of a partial plan so far, right? So decide to start navigating, then the ship stop navigating, or I guess in this case it might be the ROV. It then decide to take a sample. It finishes taking the sample. That's turned into a qualitative state plan, and then we can evaluate it, right, by using the Scotty planner. We can evaluate it exactly, right, by using the one which has obstacles. As a fast litmus test, we can relax the obstacles, and if it's not feasible, then we can rule it out, okay? So we want to be able to test consistency along the way, and we'll use Scotty path, right, to do this, but for efficiency, we'll relax the obstacles, and then we'll wait till we have a complete plan to actually using the version of Scotty which deals with obstacles as a more expensive operation, okay? In this case, the qualitative state plan imposes constraints on the dynamics, on the time, the state constraints, and the path planner is managing those, both in evaluating the heuristic and the consistency. Once you've done the heuristic forward search and you reach the goal, right? So as we're doing this, we're just going to use the relaxed planner, right, which is solving a convex problem, but it doesn't have any combinatorial part. At the point that we have a full plan, right, then we want to generate a obstacle-free path. So at that point, we call Scotty, right, with obstacles, right? So it will then do the heuristic forward search over convex regions, search for those, and then solve the convex path planning problem. Now, the one thing that I haven't then given you is how do we represent, add in, or manage temporal variables, state variables, and control variables within the plan graph, right? So conceptually what I said is that we can think of these as flow tubes. We're basically computing bounds at each event in terms of both the region that the state variables can be in, right? And then the idea in a temporal relaxed plan graph is the duration between events, right? So each fact layer maintains a set of temporal, state, and control variables, and then bounds on each of those, right? The time will be the earliest time that activity could be performed, and which we can compute by constructing the lower bound of that time given the simple temporal network. The control and state variables, we compute both a lower and upper bound by basically evolving the dynamics and the state constraints, right, to compute those bounds. And that's what I'm just showing here, which is really the N region of the flow tube in a linearized dynamics. In those cases where we have a set of quadratic constraints, just in order to be able to compute these bounds efficiently, what we'll do is we'll do a linear out approximation, right, for those constraints, okay? Once we've computed those bounds on each activity, then when we pick some activity, right, and we decide to apply it, we need to check the applicable preconditions. The fast check is to see whether or not those conditions can be satisfied given the bounds that we have on the state variables, okay? If they don't intersect, then we throw away those activities. We say they're not applicable. Otherwise, we try them, and then the path planner may say, in fact, that they're violated, okay? Once we come up with a sequence, right, so the planning process is basically identify the applicable actions, evaluate their heuristic, right? So we just need to propagate these bounds, prune inapplicable actions, select an action, right, then call Scotty convex path to compute a bound. Once we have a sequence, then we reintroduce the obstacles, right? And then we use the planner that I gave you before. And that planner then comes up with the obstacle-free region, comes up with an event schedule, a set of state trajectories, and a set of control trajectories. Okay? And we have the happy ending. Okay, so in terms of using it, right, so in Hawaii, right, we ended up using the path planner within Scotty, not its activity planner, right, but we use its path planner, right, to do a multi-vehicle mission demonstration where we were coordinating this vehicle called Sirius, which is kind of like Sentry, right, similar kind of design, right, the glider and the Falcor ship, right, and that was quite successful in terms of doing the planning, right? It actually performed very well in those realistic situations. In that case, the activity planner that we use, rather than using a generative activity planner, we use the Kirk planner, right, where we wrote a non-deterministic program representing choices of different science goals, right? And then where I showed you that stuff where we were having this dialogue, the system called Uhura, then Uhura couples into Kirk, right? So you can mix and kind of match the activity planner with the path planner, right? So then in summary, right, so Scotty takes, right, an augmented PDL domain, right, with discrete and continuous variables, right, initial and goal conditions, right, plus a set of safe regions, plus the linearized dynamics that I expressed to you with multiple influences, right, and then generates a plan, right, where the event times correspond to interesting events, either an activity beginning or end, or moving from one convex region to the next. It then generates the schedule and the set of control trajectories. Okay? So I'm just going to spend a few minutes of your break, right? But not too much, right? And then we'll break. So what is one of the open challenges to this, right? So for example, Russ Tedrick was on Enrique's committee, so as a roboticist, right? Scott kind of represents that perspective, right? And what they said there is, look, if I want to implement a particular behavior, I'll just turn it into a nonlinear program, a non-convex program. I'll use sequential quadratic programming, and that works pretty well. So this dynamic seems to be fairly simple compared to that. So still not a good enough path to actually control the robot, right? So how do you deal with that? Now, it is the case that some wisdom a year or so later, right, if you do sequential quadratic program, then sometimes it's brilliant and sometimes it's not. So it has no kind of guarantees in terms of convergence. Convex optimization does provide you that guarantee. So that's why we've stayed within convex optimization. So the idea is to think of what we've given you in terms of Scotty as a global path, a global planner. So it's planning global activities and paths, right? And it's making sure that it sees the forest from the trees, but then it works with a local planner, which is dealing with the more detailed dynamics, right? And will respect that dynamics, right, when you actually do execution. So the idea of the Scotty executive, which is what Marlies is doing, is in order to deal with a complex dynamics, what we'll do is we'll improve the accuracy of the plan just before execution, and we'll use a model predictive control approach to doing that, okay? So the idea will be that within the short horizon, right, we'll use Sulu or a convex version of Sulu, right, to plan over the short horizon, right? But then beyond that short horizon, then we'll use, normally what you end up doing in model predictive control is you use a heuristic. And the simplest heuristic is ignore the obstacles and do the chlorophyll. Instead, what we do is we use the Scotty activity and path planner as a heuristic, or the Scotty path planner, right, for example. So it computes the heuristic cost by generating a path, right, for the full horizon, right? But it can do that fairly quickly, right, as long as you remain within the convex region sequence. Okay, so we could frame these two different optimization problems and use these two different formulations. So we use a discrete time formulation in the short term, and then we use the continuous time formulation in the longer term. In the short term, right, because we're only using a linearized dynamic for short time steps or a convex over short time steps, right, we can get a fairly accurate model of the dynamics. Over the longer horizon, we've simplified the dynamics, but we don't need to reason about it as much in detail as that. So we could call those two solvers and plug them together, right? The next insight is to say, well, actually, both of those are convex problems, right, as long as we are in an obstacle-free region. So we'll actually frame that as one optimization problem. Just we discretize for a little while, and then we fix the time step for a little while, and then we allow it to vary over a longer horizon. So in fact, you can do one one combined optimization problem. And you can solve that quite effectively. So that's what Scotty path does, or the Scotty executive does. So here's just an example of the Scotty executive. So it looks like the movie that I showed you before with Sulu, right? So it has a detailed trajectory that it's executing, right? But when it does this, it's generated the full global path respecting the activity plan and the set of obstacles. And then it just constantly updates that. So it has the nice feature is that we can respect the dynamics in the short term, but we can then still think about the impact of the decisions it makes with respect to the whole horizon of the mission. Okay? So let me just summarize, right? So our goal was to develop a hybrid task and motion planner for coordinating multiple robots, right? We wanted sufficient accuracy, right, in dynamics and state constraints so that we can generate realistic approximations to global path. For a global activity path plan, I think the approximations that Scotty makes is good as long as you improve the dynamics just before doing the execution. It scales to long horizons. Key to doing this was to use both a continuous time and a continuous control variable formulation. That was enabled by doing a second order cone program, right? And then in the case of the combinatorics, by replacing a tree search by splitting on a set of variables with a heuristic forward search and then heuristics which were designed both in terms of being effective for a sequence of activities on the one hand, and then heuristics which were effective at dealing with the dynamics in the path as the other. Okay? And then this just includes some references. Okay? So with that, we'll end.
It's time to break for lunch. If you have questions, you can.
So if you have questions,